So when we talk about buffering systems, we're always talking about its acid and conjugate base pair, or its base and its conjugate acid pair. And that's going to be important because these two chemicals are going to be in equilibrium together. So there has to be an equilibrium there. Strong acid, strong bases where there is no equilibrium will not work for this system, right? So we can look at the system. We have HCN. We also have the conjugate base, CN minus. Now it's in this salt form, NaCN, because as we start in solution, the Na will dissociate off and leave the conjugate base behind. We have HF and we have KF. Again, the K will dissociate off and we'll have F minus as the conjugate base. We have HNO2, we have NaNO2, or we have the NO2 minus, which will come off this salt. So a lot of times I call these conjugate base salts because we can actually see it's just basically the salt is just a way of dissolving this conjugate base into solution because we cannot have an uncharged particle by itself unless it is in a solution. Likewise, we can also have NH3 and NH4+. Again, the Cl here is to turn this into a stable salt so we can dissolve it back into solution. And we have N2H2, and we have its conjugate acid N2H3+, again, attached to Br through a salt. Again, as long as we have this acid-base conjugate mixture, we're going to use equilibrium, switching back and forth between this acid and conjugate base, or base and conjugate acid, in order to prevent large changes in pH. Let's start with an acetic acid buffer. It's a very, very commonly used buffer. Buffer consists of 0.1 molar acetic acid and 0.1 molar sodium acetate. If 0.01 molar NaOH is added, what will be the final pH? Okay, it's a lot of information. Start with the Ka first. Okay, Ka. Water, acetic acid, H3O+, conjugate base. Now, that is going to be everything we build around. Okay. If you write any equation other than this one, you're going to end up with the entire problem wrong. So it's extremely important that we write the Ka and that the Ka is always the same. Okay, now we're going to say this is the equilibrium that we build around. The strong base that we've added in solution reacts with no equilibrium. It seeks out any acid and reacts completely. So we are going to say this happens instantaneously before the reaction even starts. This is a little bit over the top, right? But it's going to make the calculations a lot easier if we just assume it happens immediately. So that small concentration of NaOH we added was just OH minus. That's going to react with our weak acid. And because it reacts completely, it takes away the hydrogen from the weak acid and creates the conjugate base. It also creates water, but this doesn't matter. We're going to ignore that. So this is the interesting part, right? Adding base takes away from the acid and creates the conjugate base. Now, I would not write this equation again. This confuses people, but we are going to incorporate that into our ice table. So first of all, I like to set these problems up a little bit differently than the book does. So I'm going to start out just by putting in the initial amounts of acid and base from the problem. So we started with 1 molar acid and 0.1 molar conjugate base. Now, as we add the NaOH, every molecule of NaOH we add is going to react with the acid, and so we see the acid disappears, and it's going to add to the conjugate base because this acid is becoming the conjugate base as it reacts with the NaOH. So acid goes down, conjugate base goes up. And I'm adding this extra line here that you will not see in any textbook because I think it helps to organize this, right? We can see where we started, what concentrations we added, and we can see what effect adding that acid or base is going to have on our buffer. So I find that organizationally really helpful for me. Now, I'm going to point out that we have not gone to equilibrium yet. We say this is an instantaneous reaction. Now, when we're done, right, there's no NaOH left, and also our H3O+ is still 0. That hasn't changed. So our equilibrium still has to go forward. Minus x plus x plus x. We set up our Ka with our new concentrations of acid and conjugate base created from adding NaOH. Cross multiply and solve for x. Now that we have the x, we can solve for the pH. Now, One of the things I like to point out here is I like to look at what happens in these problems if we didn't have a buffer system like we do here. So if we took out the NaOH, right, if we just scribbled out this line and say we started with 0.1 and 0.1 and just solved from there, we would have gotten a pH of 4.74. Right? So when we added NaOH, we only went up by 0.09 pH, and that's pretty amazing. It's worth mentioning this concentration of NaOH we added by itself would have had a pH of 12. So the fact that we have this tiny little pH change indicates that the buffer worked. We resisted a larger pH change and had almost no effect on the solution. Okay, so a couple quick things here. First of all, work through this problem, set up the Ka first, and then set up everything else around it. I did want to point out one other thing, which is that sometimes these problems will give you moles in a solution instead of molarity. So we would just put 0.5 moles per liter, or just give us 0.5 molar. So I tried to make this really simple to point it out, but sometimes they'll say like 0.5 moles per 250 milliliters. So you have to find the molarity before you set up the equation. Again, that's annoying, so I just wanted to stop here and point that out. Other than that, just set up the Ka equation and then fit these chemicals into the Ka. Okay, so again, let's start with the Ka first. HF reacts with water. You get H3O plus and F minus as products. Now, here's where things get confusing. We've got the NaF, which is just there to hold the conjugate base. So if we have 0.4 moles of NaF, we have 0.4 molar of F minus. Okay, so we are adding NaOH, KOH, same difference. We're adding KOH. Adding base is going to react with the acid and make it disappear, and that reaction is going to create more F minus, and so the base goes up. And so we end up with more conjugate base, less acid, and then the reaction still goes to equilibrium. So now 0.4 minus X, 0.5 plus X, set up our ice chart, solve for X, we get an X of 5.44 times the negative fourth, or a new pH of 3.26. Again, if you go back and look at the old pH was 3.07. So again, we took a solution which should normally have a pH of 13, right? This concentration of KOH should have a pH of 13. Go back to look at last chapter if you don't remember. And we changed the pH only by about 0.15 points. So that's pretty significant. Okay, so this is pretty much going to do the exact same thing if we add HCl instead. So again, our Ka is always the same, acid, base, conjugate base. But now we're adding a strong acid. So it's easier to think of HCl as just H+, right? Ignore the Cl, it doesn't matter. Just H+. But that H+ is going to react with any conjugate base in solution. And so by reacting, we're essentially destroying it. But we're destroying it by adding a hydrogen. So even though we're losing conjugate base from this reaction, we're creating more of the initial acid. And so adding acid to this buffer is going to increase the acid and reduce the conjugate base. So again, I would not write out this equation, as we'll see in the next problem. Again, I would not write out the equation. I would just keep that in mind. If we're adding acid, that acid is going to add to the acidic side of the equation, and it's going to take away from the basic side of the equation. So there's that shift here. Again, the book doesn't usually show this. I like to point it out specifically. And so now the acid is going up, the base is going down, and then they still have to go to equilibrium. So now the equilibrium is going to undo a little of that. So we're going to put this in. I solved for x by making the assumption that the minus x and plus x were basically 0. Solve for x, we get 2.2 times the negative fifth. If we say that is also our H3O plus, and then we take the pH, we've got a new pH of 4.66. Again, originally our pH was 4.74. So we have taken a strong H3O plus concentration, about 0.1 molar. 0.01 molar. So this would normally have a pH of 2. And we only moved slightly more acidic by about 0.1 pH. Okay, so go ahead and try this one. It's the same problem we did before, except now we're adding acid instead of base. Again, these problems are hard. There's a ton of stuff going on. So again, we're going to start with the Ka, ignore everything else. As soon as I say Ka, I know I'm going to need this equation somewhere. So just water, HF gives us H3O plus and F minus. Now, initially, I had 0.5 moles per liter of HF, and I had 0.4 moles per liter of F minus. Again, from the NaF, this is just a salt. Put into water so it'll dissociate and give me the conjugate base. The Na is going to float away, and because it has no acidic or basic character, it doesn't matter. Now we're adding in 0.2 moles per liter of HNO3. Again, this is a strong acid, so adding it is going to react with the conjugate base and create more of the initial acid. Again, any base that's lost is going to get a hydrogen, and so it essentially becomes this acid. So acid goes up, base goes down. Now we still have to go to equilibrium. So the reaction still has to go forward because there's no H3O plus. So we can set up our Ka, 0.2 over 0.7. Again, make the assumption that these x's are basically 0. Cross multiply for x and solve 0.00238 molar. So our pH here of that concentration gives us a pH of 2.62. Now, if you didn't add in the HNO3, this pH would have been 3.07, which is a pretty big jump. But if you consider the fact that this pH for the HNO3 alone would normally be less than a pH of 1, probably about 0.8, this is still pretty well buffering, right? It's still keeping in its general correct area. So that's worth keeping in mind. All right, let's change this up. I started the work here a little bit, but we are now looking at a basic buffer. So we have some base, we have some conjugate acid salt. Again, the Br minus isn't going to do anything, and so that 0.2 molar NH4Br just becomes our conjugate acid, right? Now think about this. We're going to add in HCl. How is adding HCl going to affect the base and the conjugate acid? So think about this for a minute. See if you can figure out what the acid is going to do here, and then if you can, solve the problem. If not, we'll walk through it. So, because we're adding HCl, that HCl is going to react with any base in our solution. And as a result, it's going to give that base a hydrogen, and it's going to change into a conjugate acid. In this case, our base is NH3. When NH3 gains a hydrogen, it's going to become NH4+. And so what we are going to see in this case is that the base concentration is going to go down, the conjugate acid concentration is going to go up, but the OH minus will not be changed because all of that acid is consumed. So we don't form any plain H+, we don't lose any plain OH minus, we just assume those concentrations are still at 0. And now we are at equilibrium with our buffer system. The reaction has to move forward to create OH minus. And so we can just solve, right? We know after the acid is reacted, we have 0.15 molar NH3 left, 0.25 molar NH4 plus. We can put that into our system. We can go ahead and make the assumption. We can solve for our OH minus. Use the OH minus to get the POH and then the pH. And if we compare that to what the pH of the buffer system would be without HCl at all, so the system without HCl would have a pH of 9.26. The system with HCl had a pH of 9.03. So sure enough, adding acid made the pH more acidic, but it's a relatively small change. The HCl on its own would have had a pH of about 1.3, 1.4, somewhere in that range. We absorbed that pH, we absorbed that acid, and ended with a pH of 9, a pH change of only 0.2-ish points. So all in all, we can see that the buffer did resist pH changes. Again, there is always going to be some pH change, but that pH change is small. Again, just for clarification one more time, an acid added is going to react with the base. and create more conjugate acid. Go ahead and try this problem. Think about the K value given to you and what that tells you about N2H4 and what the equilibrium equation has to look like. And then figure out how N2H5Cl and NaOH affect those concentrations. So again, the problem here is we have a lot going on. We're given the Kb for N2H4, so I'm going to start there. I've got my Kb equation set up. H2O plus N2H4, I get OH minus, and my conjugate acid N2H5. I've got 1.5 molar N2H4 to start. And I've got 1 molar N2H5Cl, which again is going to dissociate in water and give me that conjugate acid. And then I'm going to add in the base. Now, bases are going to react with acids. So if that NaOH reacts with N2H5, it is going to take that N2H5 out of solution. And because it's removing a hydrogen as it reacts with that conjugate acid, that's going to leave me with more original base. So my base concentration goes up, my acid concentration goes down. Again, anytime you add a base, it's going to move equilibrium towards the basic side of the equilibrium. So at that point, the base is completely reacted. The buffer system, it can now move forward into equilibrium. So my reactants go down by X, my products go up by X, and now I'm set up to solve for my X. I have my Kb, I have my N2H4 concentration, I have my N2H5 concentration. I make the assumption, I solve for X, which is my concentration of OH minus, I find the pOH, and from the pOH, I get the pH. Again, if we go back and just erase the line where we added in base, right, and keep our initial concentrations at 1.5 molar and 1 molar, we would have had a pH of 8.93. With the NaOH added, my pH is 9.17. So again, the pH has gone up a little bit, which makes sense. We added base, the pH went up, right? But it's a relatively small change. Again, this NaOH concentration would have had a pH of somewhere around 13.3, 13.4. We had a much smaller change than that because the buffer absorbed that base and made a small change to the buffer system, which kept the pH in more or less the same place.